Yeah, thank you, and thank you for attending. So yeah, today I want to talk about traffic speed modeling and how we integrated the results in an open source routing engine, openrouteservice, to improve traffic speed, travel time estimation. So what's the problem? I guess as you are at the free and open source software conference, you know that there are alternatives to Google Maps. So when you want to calculate a route from A to B, there is different open source alternatives. So for example, when you go to openstreetmap.org, you will get the functionality to also calculate a route using different profiles, so by car, by bike, or walking. And you can even select different routing engines. So there's, for example, Grasshopper, open source routing machine, or Valhalla. In addition to that, there's also other ones. So for example, openrouteservice, which is an open source routing engine that's maintained and developed by Hygit. And there's different also mobile apps which let you calculate routes while you're, for example, hiking or also driving. Now, they do a very good job nowadays of calculating good routes. But something that they're very bad at handling still is these kinds of situations. So when you have to go from A to B, maybe in the morning, during rush hour, you will get stuck in a traffic jam because these open source routing services that we have nowadays don't include traffic information as, for example, Google Maps does. So why is that? The problem is not that routing engines or open source routing engines are not able to handle traffic. So there are actually some engines like Valhalla who support traffic speed data. Grasshopper also had an implementation which is not open though, or open source routing machine has an experimental implementation, and OpenRouteService also has a support for here data. The problem, however, is that these require actually proprietary data sets from, for example, from TomTom or from here, and they are very expensive, especially if you want to cover large regions. It's not really feasible for an open source project to buy such kind of data. But what about open data? There are municipalities, organizations who do publish traffic data. The problem here is though that it's always very limited, so only limited to a certain area, maybe a city. And data-wise, they're also very heterogeneous. Yeah, that's better. Different time periods, different data structures, and oftentimes it's not available for automated download. So if you want to operate a routing engine or a service, you cannot have someone manually always download the data and assimilate it. So it's just not a viable solution. However, there is a data set now that is a lot better that we had before, and that is a data set provided by Uber Movement, which is an open data set on historical traffic speeds per hour per street segment. So I guess you know Uber, like the service where you can get a taxi using your smartphone and someone will come pick you up and drive you where you want to go. And similar to Google Maps, Uber collects data from their app users. When they drive along, they collect the GPS trajectories, and from this data they derive traffic speed statistics. For example, the mean speed, the median speed for a certain street segment. They publish the data also. It's available from January 2015 to March 2020. It's all, however, only available for 50 cities worldwide. So it's not like Google Maps, which has a larger coverage. And the very good thing about this is that the data is actually based on the OpenStreetMap road network. And since most open source routing engines also rely on OpenStreetMap, this makes it very convenient because you don't have to do any map matching. So we thought that's actually a very good starting point, but usually we want to cover more than 50 cities. Yeah? There's a lot more cities where you have difficult traffic. I guess actually every city kind of has a traffic problem. So our goal, or long-term goal, would be to have, is it possible to have a global open traffic data set which is available to everyone and especially also suitable to integrate in routing engines? So the research questions that we still have to answer in order to get there are, first of all, is it possible to model traffic speed based on open data? or can we model it in a way that is good enough? And more specifically, we wanted to, in this study, look at what's the potential of social media data. So is it possible to get the spatial temporal information from the Twitter data? And the third question is also, it's nice to have a good model, but does the model actually improve the travel time estimation, or does it not? So this is our setup. As I said, we use Uber traffic speed as a reference data to then train different machine learning models for 10 different cities. We extracted them from the Uber data. And then based on that, we get traffic speed data, and that will then be integrated into openrouteservice. Now, talking about the input data, as I said, we're only using open data sets that should be ideally globally available so that we can also then apply the model globally if possible. So as actually studies before, I mean, we're not the first ones who use OSM data to model traffic speed. There have been others. So the obvious thing is to use the OSM tags, so the highway tag or the max speed tag, which already gives you some indication about how fast can I go. Then the hour of the day is also included. This is already in the Uber traffic data set, of course. And then additionally, we're also looking at social media data and centrality. So for social media data, we use Twitter. And there have been other studies who have used Twitter data before to model traffic, but they usually rely on the content of the tweet. So either they use the image to detect cars or something, or they use the text to extract important words like traffic jam. We didn't do this. We only used the location and the timestamp of the data, because we want to actually have a method that can be also applied to other data sets and is not bound to Twitter. And the whole assumption behind is actually that we use the Twitter data, or the spatial temporal distribution of the tweets, as a proxy for human activity. Because if there are a lot of tweets in an area, it means there are humans, and these humans need to have gotten to this place somehow. So they need to have used some kind of mode of transport to get there, which in turn, of course, generates traffic. So from the Twitter data, we calculated different indicators that are based on different spatial aggregation and different temporal aggregation. Spatially, we look at one street segment, and then we calculate the tweets within a 50-meter buffer, 100-meter, 250, and 500-meter buffer. And regarding the temporal aggregation, we look at all the tweets in the whole time period, and we also aggregate by tweets per hour to retain the temporal information. So how many tweets did we download? It was quite a lot. We only looked at the time period between January 2018 and March 2020. And as you can see, the number of tweets is very different, but you definitely have to interpret the numbers in relation to the population density. So for example, Cincinnati is 160,000 tweets. Berlin is 418 tweets, so it seems like, oh, Berlin has more data. But if you look at it in relation to the population density, Berlin has 3.5 million inhabitants, while Cincinnati only has like 300,000. Then the second indicator that we're also using is centrality. Centrality as such is actually an indicator which has been developed for doing network analysis in general. Originally, it comes from social media data analysis, and it will give you an indication of what is the most important edge or node in a network. So in social networks, it will be a very important person who links different communities, for example. In a road transportation scenario, it would be a very important road that maybe connects two different villages, or, for example, a bridge, because there's not really an alternative way to go. Calculating centrality, however, in a spatial or geospatial case does not make sense as it's done in the original case. Originally, centrality is calculated by calculating all routes between all nodes in a network and then calculating how often one edge or node is used, basically. But humans don't move around in space evenly, but they move around based on where they live and where they want to go. So that's why we base our centrality indicator on population data, the population density, based on the global human settlement layer, and points of interest from OSM. Good. A few sentences about the machine learning model. It's a quite simple approach, which is using random forest, XGBoost, and some optimization algorithms. We're not using graph neural network because in this case it was more about finding out, okay, which features are good and learning about the potential of Twitter data. And also graph neural networks require a lot more training than we had the capacity back then. So looking at the results, first of all, we look at the accuracy across the cities. So the rows are the different cities that we trained the model on, and the columns are different models or models with different features. So the first one is basically the baseline model. It only takes into account the highway type. The second one also takes into account the max speed tag. The third one, the hour of the day. The fourth one, the centrality indicator. The fifth one, the centrality and the tweets per hour. Then the tweets per the total tweets, and the last one is only taking, like centrality is missing. So what we can see is, first of all, from left to right, the root mean square error decreases. So our model gets better the more indicators we add. And what we can also see is that Twitter data improves the model a lot more than the centrality indicator. I think you cannot read it, but you can also look it up in the paper. And what we can also see is that, so Twitter indicator is more important than the centrality indicator. However, in cities where you do not have such a high Twitter density, the centrality indicator actually leads to a bigger improvement. So for example, you can see that when you compare London and Berlin, for example, in London you only get an improvement of 0.04 if you add centrality in addition to the tweets, while in Berlin you get actually an improvement of more than 1.0 when adding centrality. Yeah?
Sorry, what is the model targeting? Is it speed traffic in general, or you have a baseline just based in Uber and then you're trying to target it using centrality and Twitter data?
You mean what the target variable is?
Yes.
Yeah, the target variable is the traffic speed in kilometers per hour. Based on, yeah, Uber data is the reference data. So we just check and we use the open data set to model. Yeah, thanks for the question. Then looking at the residuals, so we're now comparing basically our reference data, the Uber data, to the model speed data and see, okay, how are the deviations? And in this case, we only look at roads which have the tag highway construction, so construction sites. And again, we have different models with different features. On the top left, you see the baseline model that only takes into account the highway tag and the max speed tag. So it's basically the model always predicts the same value because it doesn't have any other information. And you can see it's not a good model. A good model would be if all the points are aligned on the diagonal. But as you can see again, if we add more features, the points gradually more and more line up along the diagonal, so our residuals decrease, our model gets better. And we see again that with Twitter data we get a lot better results. So for example, the lower right, and even we can cut the root mean square error in half by adding the Twitter data compared to the baseline model. And still the best model is the one which also takes into account centrality by marginally better. And this actually we also see for streets Living Street and Trunk, and this is actually quite promising because construction sites are often the cause for traffic congestion. So we, however, don't see improvements for all street types. So residential areas, for example, the model doesn't improve anything. It's still a cloud, and it doesn't give us any information. Then we looked at different Twitter indicators. Thanks. Different Twitter indicators, as you remember, we aggregated spatially using different buffer distances from 50 meters to 500 meters, and we aggregated by hour and by the total tweet count. And in the figure you can see always for example, the first column is the 50 meter tweets per hour, and then 50 meters tweets total. And this is always showing you the difference in root mean square error compared to the model, which takes into account the tags, the hour of the day, and centrality. And long story short, the total tweet count is always a better measure than the tweets per hour. So we can learn that the spatial information of the Twitter data is more important than the temporal information, probably because the hour of the day is, there's quite a strong signal. You know that in the morning there will be more traffic than midday, for example. Also, we can see that the root mean square error decreases with a increasing distance to the road. So if we take into account all the tweets within a 5 meter buffer distance of a road, we get a better indicator or a better model performance than if we only look at the ones within a 50 meter distance. Okay, then just about the feature importance, it's actually just that they're all quite equal, except for the max speed tag, which is more important with higher traffic speeds, so at motorways. So these are the results of our model, and now let's see what effect does that have when you integrate the data in our route service. So as I said, openrouteservice is based on OpenStreetMap data, and in addition we provide with a CSV file which contains the traffic data, and it's for each line you indicate the ID of the way, the OSM ID of the way, the start node, the end node, so you can do both driving directions and single segments, and then you indicate the hour of the day and the speed value. And if you request a route from OpenRouteService, you also indicate your arrival time or departure time, and then you will get different routes depending on when you drive. So how did we evaluate this? We basically compared it to the Google Routing API, because they obviously have the best data at the moment. They don't publish it. But what we did was we created random routes using the Google Routing API, and then tried to reproduce the same route using OpenRouteService. And there we used different versions of OpenRouteService. So for example, we took the original one without any traffic data. Then we used different modeled traffic speed, so the mean modeled speed, the median, the 85th percentile. And then we also used the Uber raw data, so not using any machine learning, just the raw data that you already get from Uber. And then we calculated differences in travel time and looked at are they increasing or decreasing. We did that for 3 cities. So for Berlin, for example, we can see the first one, this is the difference in duration in percent. And this one is OpenRouteService without any traffic speed data. And there we see, okay, we have generally a 7% overestimation of travel time in Berlin. If we add the model data, we're actually not improving. Yeah, we're actually making things worse. If we, however, use the Uber data, the raw data, we also don't really improve it, but we're not making it a lot worse, let's say. We also have quite a lot of outliers, which is actually the case because it's not as easy to reproduce the same route from Google Maps using OpenRouteService, because you have to give waypoints, and these waypoints in between might snap to another route next by, and then we kind of do a little detour. We try to filter them out using different thresholds, but it's not always possible. Then for Cincinnati, things are actually becoming more hopeful. So it was not all for nothing. So we do have an overestimation again if we don't use any model speed data. With the model data, it does not improve at first, but if we use the 85th percentile speed, it actually does improve a little bit. And using the raw data, it actually, does improve considerably. For Nairobi, we at first have an underestimation, and then actually we improve things a lot, and really even using the model data or the Uber data gets a big improvement. So concluding, traffic speed modeling, what we learned, first of all, Twitter has a big influence on the model performance. Also, the geographically adapted centrality does improve the model, especially in cities with not much Twitter data. From Twitter, we use the spatial information in the wider neighborhood is most important, and the improvements vary by road traffic, road type. Then the traffic integration showed that the traffic speed data did not improve the travel time estimation in all cases. And if it did, the 85th percentile was actually the best choice to use. And we also might not need traffic data for all edges, because sometimes the Uber data already improves the model, and the Uber data is only available maybe for 40% of the streets, while the model data was available for all of them. And also we see that regionally we have differing biases in travel time estimation right now. So in some cases we overestimate, in others we underestimate. So what are we going to do about this? First of all, Twitter has discontinued, or at least very much restricted, the access to the geo information. So we have to look for other data sets, other social media platforms, or mobile phone data. Furthermore, we'll investigate the adaptation of the centrality indicator to the geographical domain. And then also using graph neural networks, which have come up a lot in the last 2 years for traffic speed modeling, should be investigated. And also the transferability to other regions, so that at some point we can really go beyond these 50 cities where we have data at the moment. For the traffic integration open route service, first thing we're going to try to do is adapt our, at the moment, the assumed driving speeds in ORS regionally, so we get a better result, for example, in Nairobi than before. Also, we need to improve this methodology to estimate or compare the travel time. And also, we also saw that using the Uber data structure with the CSV file is very inefficient for the RAM. So definitely adapting the structure to be a bit more efficient is necessary before we can actually release this feature. Okay, took a little bit too long, but I hope it was interesting. Thanks.